So yeah, please go ahead.
Okay. Um, Thank you very much for the organizers and everyone helping to run this. Um, and for the introduction, Tan. There's a preprint associated with this talk. So if you're interested, I'm going to give you a very, very high level overview. But please go to the preprint if you have more questions. So to give you a little bit of background, um, as many of you know, passive systems are systems that obey detail balance. And these systems have a notion of equilibrium states. And if allowed to relax freely, they relax towards equilibrium. And in fact, we can imagine that their evolution can be described, not just imagine, but we can describe their evolution as flowing down the gradient of a non-equilibrium free energy. And here, by non-equilibrium free energy, I just
Sorry, just
mean,
a second. Artemy, do you have a video? I can see your face.
yes. Sorry.
Brilliant.
Thank you. Thank you. Uh, and by non-equilibrium free energy, here I mean this relative entropy between the current state. So this is going to be a probability distribution, or it could be a concentration vector in a chemical system, or it's generally the thermodynamic state, and the equilibrium state, which I'm going to write as the x equilibrium here. And in fact, if we think about the entropy production rate in these systems, we can write it as the loss of this non-equilibrium free energy, so as the decay of it. But if we think about the evolution of the system, the state in this space, then it's easy to see that the only way that free energy can be lost is if the state x moves in the space of states. And so, in fact, the entropy production rate can also be thought of as a kind of measure of speed of evolution. And in particular, the entropy production rate vanishes only when the system is in steady state, and the steady state in these systems is also the equilibrium one. And this idea that the entropy production rate, the dissipation, actually is a kind of measure of speed gives rise to what are known as thermodynamic speed limits, and also it gives rise, can be interpreted as certain kinds of thermodynamic uncertainty relations. But thermodynamic speed limits essentially give us bounds that relate some kind of dissipation, like the entropy production rate, and some kind of measure of speed, like here, for example, the norm of the rate of change. And throughout this talk, by the way, this kind of Germanic A will indicate the activity, which is the total number of jumps or reactions per second. So it's a kind of an intrinsic time scale of the system. Now, in contrast to passive systems, active systems undergo continuous driving. So by active systems, I mean our favorite examples like ATPase, for example, which may be driven by gradients of chemical potential, and it does not relax in general to an equilibrium steady state. And if it does reach steady state, it's generally will dissipate and continue to produce entropy even in that steady state. And associated with this, so another side of this is the fact that there's no kind of there's no free energy potential that describes the dynamical evolution of the system. And as a result of this, in active systems, the entropy production rate is not a measure of stationarity. And in fact, speed limits that are based on the entropy production rate can become very weak or even vacuous. And what I mean by that is that, for example, in a system that is near non-equilibrium steady state, the right-hand side can be very, very small indeed, because, or even vanish, while the left-hand side can be very large because the system continues to dissipate. So one long-standing idea in the field that goes actually back decades and maybe even in certain forms to Prigozhin is that the entropy production can be decomposed into two parts. So one part, which is sometimes called the housekeeping part, reflects the dissipation due to cyclic fluxes that don't actually change the state. And the other part, which is often called the excess part, captures the relaxation and the non-stationarity of this state. So the housekeeping is what you need sort of to keep the house up, so just to cycle around, and it's associated with non-conservative forces. And the excess part is associated with non-stationarity, so evolution through state space, and conservative forces, as I'll mention a little bit. And it also gives rise to the idea that by only looking at this part of the entropy production, which is just the non-stationary part, I hope you can see my mouse cursor, by the way, that we can derive much tighter speed limits that don't become vacuous even as we approach, for example, stationarity or slow evolution. So this is the background. Now let me tell you kind of how our results fit into this. So first, we propose a generalized definition of free energy, which is applicable to a very broad range of active systems. This includes linear systems like Markov jump processes. It includes nonlinear systems like chemical reaction networks. And we use this definition to define a notion of excess entropy production and a notion of housekeeping entropy production. And we show that this decomposition applies to many kinds of systems where previously it was not possible to define a well-behaved, non-negative, a finite notion of excess and housekeeping. So this includes arbitrary nonlinear systems, and this includes things like systems with odd variables like momentum and velocity and so on. And as one application among others, we derive some thermodynamic speed limits, which can be tight even in the far from equilibrium regime and even for nonlinear systems. And I believe they actually are the kind of first speed limits of this type that can apply, for example, to deterministic chemical systems, even when they're driven very far from equilibrium. So let me run through our formal setup and the main tool that we use. So we begin by considering a discrete state system whose state is given by x, and the state evolves according to this discrete continuity equation. Basically, we can think of it like that. So here, J is a vector of one-way fluxes. There's an element of J for every one-way reaction or every one-way channel or way of transitioning between states. And nabla here is the stoichiometric matrix. It just tells us which fluxes affect which states and transport either mass or probability between which elements of X. Within this formalism, we can write the entropy production rate purely in terms of the fluxes. If we define for the forward fluxes a set of paired reverse fluxes, which I write as tilde J, we can write the entropy production rate as this kind of log ratio between the forward and the backward fluxes, which I think is very familiar to many of you. And we can further write this as a generalized relative entropy between flux vectors. So this is a relative entropy in the space of fluxes, not in the space of states. And it has this form, and it reduces for systems without odd degrees of freedom. It reduces actually to this familiar Schnackenberg type form. And after it's this kind of standard setup, we use a variational expression of relative entropy. So we write relative entropy as a solution to an optimization problem. And this variational expression is well known actually in, for example, large deviations theory. And basically, if we write it like this, as this optimization problem, the optimal vector actually gives us the thermodynamic forces here. So the thermodynamic forces are given as the log ratio of the forward and backward fluxes. Now, in passive systems, the thermodynamic forces actually can be written as the discrete gradient of the free energy, or this kind of pointwise free energy. And so we can reduce the optimization problem to the subspace of forces that have this form without losing anything, and we still recover the full entropy production. And we now optimize over sort of state observables, and if we do that, we recover the free energy, the usual free energy state observable. But for active systems, we cannot write. In fact, they're kind of defined by the fact that the forces are not conservative, so we cannot write the forces in this way, but we can still consider this restricted optimization problem. So we can still optimize over the observables that have this form. So basically we search over state potentials. And as we show in our paper, what we recover here is an expression which reflects the speed of evolution of the system, which is probably not obvious if you look at it in this form, which can be understood as the excess entropy production, which vanishes in steady state, and whose optimal potential actually gives us the generalized free energy, which reduces to the usual one in the case of a passive system. So as one application, we derive a tight thermodynamic speed limit, which here is stated in terms of the Wasserstein one distance, which is a kind of natural measure of distance for discrete systems, which takes into account the topology of the system. And we give a number of interrelated interpretations of this quantity, which if you're interested in things like optimal transport or large deviations, or information geometry, I invite you to look at our paper. And we show that it gives this quite meaningful decomposition into excess and housekeeping parts, where the housekeeping captures the non-conservativeness of the forces. So I have two examples here, but I think to save a little bit more time for questions, I'll just go over one of them. So this is a unicyclic system where we show we recover quite different results from the Hatano-Sasa adiabatic, non-adiabatic approach. The example I want to focus on is the brusillator. So this is a well-known deterministic chemical system with two species that undergoes oscillations. And what we show here is that we can decompose the entropy production into excess and housekeeping as a function of the two concentrations. And we show that the excess really recovers the relevant dynamical features in this system. For example, it recovers the location and shape of the limit cycle, and it recovers the kind of slow manifold that crosses the limit cycle, and so on. And finally, we show that we can actually compute a thermodynamic speed limit on the time needed for the system to complete one cycle. And given this actually applies to any chemical oscillator or speed limit. And for the brusillator, even though it's very strongly driven, it's only 2 or 3 times away from the fundamental bound determined by our speed limit. So this is one example application. So thank you very much. These are my wonderful collaborators on this project, and maybe we have time for a question or two.
Yeah, thank you.